In the previous video, we looked at conformations of ethane and introduced the terms conformation, torsional strain, staggered, and eclipsed conformations. In this video, we are going to look at propane and butane and higher alkanes. So with propane, we have a 3-carbon alkane, and we can look at different conformations using Newman projections. So in this case, we need to define which carbons we're looking at. So we can call this one our front carbon, and this one is our back carbon. So if this is the back carbon, then we're going to have 3 groups coming off the back carbon. And then our front carbon, I want to draw an eclipsed conformation as well as a staggered conformation. So looking at our front carbon, in addition to the other carbon that's already part of the Newman projection, this carbon is connected to hydrogen, hydrogen, hydrogen. So that's what we need to fill in. So our front carbon is connected to an H, and an H. In our other conformation, this is still our front carbon, so we fill in our H, H, H. Looking at our back carbon is connected to hydrogen, hydrogen, and methyl group. So that's what we need to fill in. So our back carbon has, let's say this one is a hydrogen, this one is a hydrogen, and then back here is a methyl group. Over here, let's say this is our methyl group, hydrogen, and hydrogen. So we still have a staggered conformation and an eclipsed conformation and an infinite number of conformations in between. So in the case of ethane, we had our energy diagram that looked like this. Because propane will have a higher amount of strain in an eclipsed conformation, then maybe that would look more like this. Right? So it's going to be a little bit higher energy as we get to our eclipsed conformations. So it'll be a little bit higher energy, but still we have free rotation around the carbon-carbon bonds. Next, let's look at conformations of butane. And to begin with, we are going to focus on staggered conformations. And in particular, let's focus on the C2-C3 bond. So imagine that we are looking down here. Let's call this one our back carbon, and we're going to draw 3 Newman projections. So here's our first one, second one, third one. And our back carbon, we can have our methyl group straight up and our hydrogens down. Let's keep that the same. Methyl group up, hydrogens left. Then this is our front carbon. Here's our front carbon, and it is a staggered conformation. So we have one atom here, one here, and one here. Let's say we start out with this as our front methyl, hydrogen, and hydrogen. Now let's imagine that we take our red carbon and we rotate it this way so that we get this CH3, here's the H, and then continue rotating this way, which will give us the methyl group here, hydrogen, and hydrogen. So here we have 3 different staggered conformations. In each case, the front bond bisects the angle created by the back bonds, so they're all staggered. Because they're staggered, they have torsional angle of 60 degrees, which means no torsional strain. But there is a difference between these conformations. Looking at the central one, this methyl group is as far as possible from the other methyl group. Looking at the conformations on the left and the right, this methyl group is closer to the back methyl group. And if you were to look at a full model of this, you would see that we actually have a little bit of crowding between these methyl groups. So this is called van der Waals strain. and this is our second type of steric strain. So remember, our first type was torsional strain. Our second is van der Waals strain. So all three of these are staggered, but there is a difference between them, and so they get different names. The first one is called a gauche conformation. So this is where the methyl groups are closer to each other. So it's staggered and a gauche arrangement between the methyl groups. This one is a staggered conformation and an anti-arrangement between the methyl groups. And the third one is staggered and gauche, because again, these methyl groups are close to each other. So the different staggered conformations are going to have different energies because of the absence or presence of van der Waals strain. Next, let's look at eclipse conformations of butane. So let's keep the back carbon the same way: methyl, hydrogen, hydrogen, methyl, hydrogen, hydrogen, methyl, hydrogen, hydrogen. So this is the back carbon, and then this is the front carbon. So we are looking down the C2-C3 bond, our front carbon. Now, this is an eclipse conformation. So one possibility is that we have the methyl group eclipsed with a methyl group, hydrogen over the hydrogens. Next, imagine that we rotate around here, and then that will bring us to the next eclipse conformation where the methyl group is eclipsing the hydrogen on the right. Here's hydrogen, here's hydrogen, and then continue rotating around clockwise, and then we will get to this methyl in front of the hydrogen, this hydrogen in front of the methyl, and this hydrogen in front of a hydrogen. So here I'm drawing them almost completely eclipsed because I'm using different colors and because I'm talking you through it. Normally what we have to do is, even though what we want to draw is something that is completely eclipsed, we have to draw it a little bit offset so that our drawing makes sense. So maybe we have our back carbon like this, and then we have our front carbon, just a little bit tilted so that we can actually read whatever substituents we have here. Just try to be clear with your drawings. Now, when we compare the eclipse conformations of butane, because all three of them have torsional angles of 0 degrees, then there is lots of torsional strain. In addition, all of them have van der Waals strain. Here we have our methyl group too close to our hydrogen, methyl too close to our methyl and hydrogen are too close. Here we have a methyl, and here we're going to have a lot of van der Waals strain. On the previous slide, we saw that the different staggered conformations were called gauche and anti. Unfortunately, there isn't a name for these, but I like to call these eclipsed. So that doesn't give us any more information, but this one fully eclipsed. So when we have our big groups eclipsed on each other, then we have, in addition to having the maximum torsional strain, we also have the maximum van der Waals strain. So the fully eclipsed conformation is going to be the most unstable. So let's think about rotation around the C2-C3 bond in butane. Once again, we're looking at our torsional angle from 0 to 360. Here we have our energy in kcals, or kilojoules per mole. We are starting out in our fully eclipsed conformation, where the methyl group is eclipsed on the other methyl group, and this is the highest energy because this one has torsional strain and van der Waals strain. As we rotate, let's take the front carbon and rotate it around this way, then the energy is going to decrease as both the van der Waals strain and the torsional strain decreases. By the time we get to this staggered conformation, so this is a gauche conformation, we are at much lower energy. There is no torsional strain but we still have van der Waals strain. Continue rotating and we get to an eclipsed conformation, but here we have our methyl group eclipsed on a hydrogen eclipsed on our methyl group. So it is high energy, but not as high as the fully eclipsed. Continue rotating and we get to our next staggered conformation, and here our big groups are anti to each other. So we are at the lowest energy because there's no torsional strain because it's staggered, and there's no van der Waals strain because the big groups are anti. Continue rotating, we get to our next eclipse conformation, and then our next staggered gauche conformation, and then back up to our fully eclipsed conformation. So the energy difference between the most stable and the least stable conformation is bigger than what we saw in ethane and what we would see in propane as well, but still the interconversion between the different conformations happens very quickly, even at room temperature. So we call this a barrier to rotation, but it's a barrier that can quite easily be overcome. Can we do the same type of conformational analysis of larger alkanes? Can we look at pentane and hexane and heptane? Absolutely. We have more flexibility. If we were looking at pentane, for example, we could specify whether we are looking down C1, C2, down C2, C3, etc. If we're looking at hexane, then maybe we want to focus on looking at this bond and seeing the different conformations around there. What about branched alkanes? If we have something like this and we have another methyl group, if we are looking down here, so between carbon 2, carbon 3, then our front carbon is going to be connected to a hydrogen, a methyl group, and a methyl group, and then our back carbon is going to be connected to a hydrogen, and an ethyl group. So we can still do the same conformational analysis. We can draw our Newman projections. We can imagine rotating around to see the different types of strain that would be possible. Now, one thing that I just wanted to mention, no matter how big the molecule is that we're looking at, the one common feature is that the anti-conformation is going to be the most stable. And so what I've drawn here as the zigzag, well, if we're thinking about this bond, we can see that we have the anti-conformation. So, we talked about using the zigzag as a convenient shorthand, and it also helps us to think about the tetrahedral arrangement around each atom. But now we see that it also can help us to remember the most stable conformation is going to be anti. So all of the conformational analysis that we've done on ethane and propane and butane, those can absolutely be applied to much larger molecules. This wraps up what we're going to do with alkanes, and in our next video, we're going to look at conformations of cycloalkanes.